Hi guys, and welcome to our Wadix Technologies YouTube channel. Wadix Technologies is a company specialized on embedded systems training and online coursing. We offer a big variety of free online courses specialized on embedded systems technologies. All of this is within our YouTube channel. We provide as well blogs, articles, advanced online courses, and one-to-one training services specialized on embedded systems technologies within our website www.wadixtech.com. So don't forget to hit the subscribe button of our YouTube channel, as well as checking out the different services we offer within our website wadixtech.com. In today's video, we're gonna cover the CONST data type qualifier in embedded C programming. We'll see how we can mark a variable using this data type qualifier and what will be the characteristic of this variable. We'll see as well how we can utilize the CONST data type qualifier with pointers. And we'll see as well where, in terms of physical memory, those const variables will end up. And we'll finalize our video by a demo project where we're gonna inspect a real embedded systems based binary, and we'll see where those const variables end up. This is an example of the syntax to be used to mark our C variable as const. Const is a data type qualifier. It is not a standard C data type. So it is used to mark a already declared C variable as const. So it is not aimed to replace those C standard data type. So first of all, you will need to declare a standard C variable, and you will need to specify, of course, the data type of this variable. In this case, it is an integer, and the name of this variable. Then you will need to initialize your variable during the declaration. And finally, you will need to mark your declared variable as const. The initialization of a const variable is done during the moment of definition of this variable. So we cannot overwrite the content of this variable later on within our C program. If we try to do so, then the compiler will throw an error saying that this variable is already marked as const, and hence we cannot override it and initialize it again. Once we have declared our C variable or buffer and mark it using this const type qualifier, we cannot modify it anymore within our C program. This is what is called immutability. Means any attempt to reinitialize or access this const variable or buffer will cause a compile time error. So the initialization of this const variable or buffer to be done only once at declaration time. So no runtime initialization is supported for const variables and buffers. If we are marking our variable or buffer to be const, then this means we don't have any intention to modify it within our C code. And hence, from readability perspective, it's quite clear to the user and developer that this variable or buffer that is marked as const will not be modified. And finally, marking a variable or a buffer as const enable the compiler to perform certain optimization, like making the const as part of the instruction opcode. And this is quite good actually from code size and performance perspective. Now, beside using const type qualifier with standard variables and buffers, we can utilize as well const with C pointers. Pointers in C are just memory addresses that contain the address of other variables, as you can see here. And this is the way we can reference and point to the content of other variables. So we can access those variables via those pointers. Now, if we try to deploy and associate the const type qualifier with pointers, we'll end up by 3 use cases. First of all, we can have pointer to const. And this is an example of a pointer pointing to a const integer. This means here that the pointer itself can be modified. However, the const integer variable that we are pointing to cannot be changed. In reality, this means that this variable or the content of this variable cannot be changed, so it will be always fixed. However, the pointer itself can be pointing to other variables, so it can be updated. And the update is done by changing this address contained within this pointer by another variable address. And with this way, we can enable our pointer to point to different variable. Second use case is const pointer. And this is an example of a declaration of const pointer to an integer. Now, this second use case is the other way around from the first one. So the pointer itself cannot be modified. However, the content of the variable that we are pointing to can be changed. So in reality, this means that this pointer cannot be changed, and hence it will be always pointing to this variable. However, the content of this variable can be changed and modified. Finally, we'll have const pointer to const. And this is an example of a const pointer pointing to a const integer. This means that we cannot modify neither the pointer, neither the variable we are pointing to. So here, we cannot modify the content of this variable, and here, we cannot modify as well the content of our pointer. This means it will contain all the time the same variable address, and hence it will be always pointing to this one. When it comes to embedded systems programming, and to be more precise, embedded C programming, what matters by the end of the day is the memory location where our variables, functions, and code will end up, as well as how the processor will be able to execute our program instructions. Now, if we have declared a const variable, then most of the time our const variables must be located in the same memory as our code. This is due to the fact that our code in most of the time will require direct access to those const, and hence having those const located close to our code will facilitate this access and will optimize the access time to those const from our code area. Hence, instead of inserting certain jump location or winner to access those const from our code, we can just embed even those const variables as part of the code instructions. Now, in terms of hardware, the code and const variables will be located in general either in flash memory or ROM, read-only memory. However, there is nothing that prevents us from locating those const variables within RAM. However, from use case perspective and as a recommendation, you should always place your const variables as part of the memory where you are having your code. When it comes to the linking stage, the linker will place those const variables and buffers in general within the section that is named read-only data. So this is the section label that will be associated to each of our const variables. However, and this depends from your toolchain and compiler, the linker may place those const variables as part of the text section. So this is the same section as your code. Or may use basically this const data section label to mark your const variables instead of the read-only data. However, in most of the cases, this read-only data section is the one to be used to label and mark those const variables. And hence, you can even place your const variables in different memory using basically this section prefix. As stated here, in general, we'll have our code marked with the section name prefix and our const variables marked either with this read-only prefix or const data prefix. One of the reasons why we are having separate section names for our code and read-only data or const, even if they're gonna be placed within the same memory area, is that we want to prevent executing in accidental way our const, and hence we want to prevent that the processor will consider those const variables as instructions. Therefore, we can place those const variables slightly far from our code. So both can remain within the same memory area, but place it slightly far away so that the CPU cannot execute accidentally those const variables while it is executing the normal code instructions. Also, it is better to read basically the placement of our const variables using this section prefix rather than having a single section name for both code and const. It means if you are parsing your map file or even your linker script, it's easy for you basically to spot the location of your const variables compared to the code if it has its own section name prefix. And finally, as stated before, the recommendation always is that your code and const variables must be placed within the same memory area. And in general, this memory will be either ROM or flash for small embedded devices like microcontrollers. And to spot the location of your const variables, it is recommended to inspect the map file generated by your linker. Now, as you can see here, this is a basic makefile project that has been adapted to work on an ARM Cortex-M microcontroller. And to be more precise, this has been adapted for an STM32 based platform. As you can see here, I'm gonna use the ARM non-EOB GCC compiler. And this compiler is dedicated for ARM Cortex-M based microprocessors. I'm gonna utilize as CPU target the Cortex-M3, and for the linking stage, I will need the linker script to enforce the placement of the different sections within our code in different memory areas, like placing the text and the read-only data within flash memory and the data and BSS within the RAM. And finally, I will generate this map file that allow me the inspection of the final location of the different binary sections, whether it is text, read-only, or data. I have created this main.c file, and here I have declared this const integer variable. As you can see, I had to initialize this variable only once during the declaration time. Any attempt to access or modify the content of this variable later on within our code will cause the compiler to throw an error. Here I have a linker script that has been adapted for an STM32 microcontroller. So this is our flash memory and this is our RAM area. Here we're gonna place our code and const variables, and here we'll need to place the global variables and BSS section. Now the most important thing to write it down out of this linker script is that our code, which consists of set of functions, will be labeled with this section prefix. And by specifying that this section prefix must be end up within this flash area, then we are enforcing the placement of our code within the flash memory. As stated within the slides, in general, the different const variables will be marked with this read-only data section prefix or const data section prefix. In some corner cases, with some specific compilers and toolchain, the placement of the const variables will be the same as code. So both will have the same section prefix, which is text. But generally speaking, there is always different label prefix for const compared to code. And here I'm stating to the linker that we should place any variable that is marked with this section prefix, either read-only data or const data, within the same code memory area, which is flash. Now back to our main function. So this is our const variable, and here we will try to access this variable within our main function. Now we'll try to compile this code, and here we go. As you can see, the compiler has thrown this error. This means that our const variable is now marked as read-only variable, and any attempt to modify or update a read-only variable will cause the compiler to throw this error. We'll revert back our code, then we'll compile it again. Here we go. The code has been compiled. Now we'll try to inspect our map file. We'll try to look for our variable or const variable. And here we go. So this is the variable. As you can see, it is marked with this read-only data section prefix. So this variable will be located within this section. And in our linker script, we have enforced the placement of this read-only data section prefix within our flash memory. And here, the variable, as you can see, it is located within the flash memory. So the same location as our code, but will have a different address.